Hey guys, welcome back to the channel. In this one, we're going to be looking at vectors. First, we're going to discuss vectors and scalars. You might have learned this in either physics or math, and let's get into it. Quantities which have only magnitude are called scalars. They only have a number associated with it, and it does not matter whether it's positive or negative. And examples of these would be speed, energy, distance, and power. You know that if I walk at 2 meters per second in the right direction, would also be the same as walking to the left with the same speed. Here, the speed is the same, but the velocity is not the same. In the first example, it's going to be plus 2 meter per second, and in the second one, it's going to be negative. This is because vectors they have direction. So quantities which have both magnitude and direction are called vectors. The examples are velocity, force, displacement, and momentum. To represent vectors, we use a head-to-tail representation. Let me show you what I mean by that. We draw a line segment and we're going to draw an arrow. This would represent the head and this is the tail. We go from the tail to the head, and that's how you represent a vector. But what is a vector? It is a scaled directed segment. It has both magnitude and it has a direction. A vector can also be this, this, and so on. We can add vectors, we can add these two, we can subtract them, and then we can multiply them too. And now we're going to look at position vectors. A position vector essentially tells you the position of the vector with respect to the origin. The origin would be 0, 0, right? And this position vector will tell you how far it is from this point. So that's what is a position vector. And it can be represented as OA, where O is this point and A is somewhere on the plane. So it goes from O to A. We have to use this arrow on top um, to tell them that it's a vector. Or we could use a capital A, no capital, sorry, bolded A to represent a vector. But while you write on the paper, it would be more convenient to write A dash or A thing. This is often used in textbooks while printing, but it's going to be hard for you to draw a bolded letter. And so we use this. This would be OA and this is A. The magnitude or length can be represented by the magnitude of this or just OA. OA would be the length and either this, or this. We're going to learn about magnitude soon, but it's like you can think of it as the distance, like how long it is. And that's what a magnitude is. And now we're going to look at AB, which is the vector AB. It's the vector which originates at A and terminates at B. Like I said, this would be the tail and this would be the head. And therefore it starts at T and ends at H. Or I mean starts at A and ends at B. And the AB is the position vector of B relative to A. Relative to A, B is the position vector. No, AB is the position vector. Usually when we say position vectors, we mean with respect to the origin. But we can also write this statement, which would also be valid. And now we're going to look at how to represent a position vector. Just imagine the point P with coordinates x and y. It has a position vector of OP. So we can represent it in two ways. The first one is called as the component form, and the next one is the unit vector form. In the component form, we represent it in a column form. The top is going to have the x component, and the bottom is going to have the y component. And we can just write this as this, which is also the same. This we represent it as the unit vector form. A unit vector is just, it has a length of 1 and is often used to tell you the direction. It's mostly to use to let people know about its direction, and it has like a magnitude of 1. Let's talk about what I and j are. Like I said, it's going to have magnitude 1. So I is 1, 0, and it is a base vector in the x direction. This is how it would look like. If this is a magnitude of 1, then this would be I, and j would be this. And that's how you plot them. I in the x direction and y in the the I in the x direction and j in the y direction. And the set of vectors I comma j is the standard basis for two-dimensional x comma y coordinate system. You can just plot it like how you would normally do. Let me give you a few examples. So we have to first represent the following vectors. Let's do that. Let's use a different color. For A, we have 2i minus 4j. You know that I moves in the x direction and j moves in the y direction. So we just have to plot 2 comma minus 4. This is 2 comma minus 4. 2 minus 4. This would be A. Let's plot B. This is 5 comma 6 because both of them are positive, so it's going to be 5, 6. This is B. I'm writing capital, but you're supposed to write lowercase. And then we have this. It's going to be negative 4 comma 3. Negative 4 comma 3 would be 3 up. This is C. Now let's do the last one. Minus, okay, look at this. This is J, right? So it's going to be, wait, let me use a different color. Purple. Okay. This is going to be minus 8 comma minus 9. This is because this is I and it's going to have the x coordinate, and this is y, so it's minus 9. It's minus 8 minus 9. It's going to be somewhere here. This is D. So this is how you represent vectors. I hope it was simple. It's just like plotting the x and y coordinates. Now we're going to look at vector equality. Two vectors are equal if they have the same magnitude and same direction. Essentially, their x components must be equal and their y components must be equal too. And equal vectors are parallel in the same direction and are equal in length. The arrows that represent them are translations of each other. Alright, so this has the same magnitude as this and this, and they have the same direction if you look at it. And therefore, these three vectors are equal. If you have this one, let's say this is B, this is not, these two vectors are not equal, but this would be, because they have the same magnitude and they have the same direction. And if they were like in opposite directions, this would be minus A because they're negative vectors. We're going to talk about that soon, but just remember that if it has the same magnitude but opposite direction, it's called as the negative vector. And this would be negative B. It just means that it goes in the opposite direction. Okay, yeah, it's right here. It's negative vectors, right? So AB vector and BA vector have the same length, but they have opposite directions. We say that BA is the negative of AB. So therefore, we write this. When we break this down, you'll understand why this is that way. You may not understand this right now, but you'll understand why this is when we do, I think, the subtraction and addition of vectors. But I'll just tell you how this works. So this is OA minus OB. This would be minus of, this would be OB minus OA. This would be OA minus OB. These two are the same, right? And hence, this is in fact true. And A and minus A are parallel and equal in length, but opposite in direction. That's what a negative vector is. They're same magnitude, same length, but opposite direction. I'm hoping that these concepts are clear. And now it's time to move on to the questions. Let's read the first one. We have to write the illustrated vectors in component form and in unit vector form. All right. So we have this. So first, let's say this is 0, 0. It's not going to be, but let's just consider that. And now we have to find the length in the x direction and the length in the y direction. So this is going to be 1, 2, 3, 4, 5, 6, 7. So therefore, it's 7i because this is I, and so on. And now let's look at the y direction. It's going to be j, j, and j. And therefore, it's 3j. In component form, it would be 7, 3. 7, 3. And in unit vector form, it would be 7i plus 3j. Let's look at this one. This will be minus I because it's in this direction, in the left direction. This is minus I, minus I, minus I, minus I, and minus I. We have 1, 2, 3, 4, 5, 6. So it's negative 6i. And there's no y component, so it's going to be 0j. In component form, it would be minus 6, 0. And in unit vector form, it would be minus 6i plus 0j. We have to write in component form and illustrate using a directed segment. So the first one, let's use purple. We have to write in the component form. So it's going to be 1, 2. And this is going to be simple. This is I, J, and J. So therefore, this is going to be this is vector A. And now let's look at this. This is minus 1, 3. Minus 1, 3. You just think that's a straight line. Yeah. Okay, that's B. Now let's do C. Minus 5. This is easy. Just a straight line. This is C. This is going to be 0, minus 5. and we have to write down the negative of this. It's just going to be -1. We just have to put negative, 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 plus, negative, negative, plus. You just have to negate it, and that's all. The next topic is the magnitude of vectors. So first consider the vector 2i plus 3j. The magnitude or the length of A is represented by the symbol modulus. I'm pretty sure we learned this in either functions or quadratics. And by Pythagoras theorem, we have A squared is 2 squared plus 3 squared, which is 13. So therefore, the magnitude of A would be root of 13, because the length is always going to be positive. We're not going to have -13 units. And therefore, it's going to be plus root 13 units. So this is the general formula. If A is A1i plus A2j, the magnitude or length of A is the square root of A1 squared plus A2 squared. It's just like finding the Pythagoras theorem. And if we've understood that, let's solve the questions. We have to find the length of this. So it's the square root of 1 squared plus 1 squared. We have square root of 1 plus 1, which is square root of 2. This would be square root of 5 squared plus -12 squared. It's going to be 25 plus 144, square root of 169, which is 13. We have -1 squared plus 4 squared. It's going to be 1 plus 16, which is square root of 17 units. The next one, we have to find the magnitude. The word magnitude and length mean the same. It's going to be square root of 3 squared plus 4 squared, square root of 9 plus 16, square root of 25, which is 5. It's going to be square root of -4 whole squared plus 3 squared. It's going to be square root of 16 plus 9, square root of 25. Therefore, 5. That's the answer. We have to find k for the unit vectors. Alright, so we have to make this the unit vector. Therefore, square root of 0 squared plus k squared is 1. Let's square both sides. And k is plus or minus 1. The answer would remain the same for this also. K is plus or minus 1. Now we have to find the length of this. I think we already did this question. Yeah. Okay. Which of the following are unit vectors? Let's find this. Square root of 0 squared plus -1 squared. This is going to give us 1. Therefore, this is a unit vector. And now we have this one, square root of root 2 whole squared plus 1 divided by root 2 whole squared. It's going to be square root of 1 divided by 2 plus 1 divided by 2, which is root of 1, therefore 1. Alright, so we have the magnitude of V is root 73. So it's 8 squared plus b squared. Let's square both sides. 8 squared plus b squared, 64 plus b squared. 72 minus 64 is 9. Therefore, b squared is 9. And b is plus or minus 3. That's the answer. Next topic is operations with vectors. We have three: addition, subtraction, and multiplication. In vector addition, we just have to add the x components and then the y components. So just imagine we have the vector A, which is a1, a2, and b, b1, b2. Notice that the horizontal step for a plus b is a1 plus b1, and the vertical step would be a2 plus b2. So you just have to add these two, and then write it like this. So this is what you need to do. And this is the diagram. You can look at it. So if this is A and this is B, then the resultant addition would be this. This is A plus B. And now the x component of this would be A1 plus B1. And this would be A2 plus B2. And that's how you do it. And subtraction. So to subtract one vector from another, you just have to add its negative. So if we have vectors A and B, let's take C and D, and we have to do A minus D. We just have to find the opposite of D, or the negative vector of D, and then add that to C. And that's what they have written over here. It's A minus B is A plus of minus B. And therefore, we just have to subtract a1 minus b1 to find the x component, and we have to do a2 minus b2 to find the y component. That's all. It's very simple. And now let's look at the diagram. If this is b, this would be negative b, because it has the same magnitude but different, like opposite direction. And this would be a, and a minus b is a plus b, and therefore this would be a minus b. The final topic under this is scalar multiplication. We multiply vectors by scalars such as 2 and minus 3. And it can be any real number. It doesn't have to be like an integer and so on. So if A is a vector, we define 2a as a plus a, and 3a as a plus a plus a. And so this would be a, 2a is just going to be double of that, and 3a, 3 times of this. And if we have a negative, it's going to switch direction. If it's going this way, it's going to go back. And that's all you need to know. So 2a is the same direction as a, but twice as long as a. 3a is the same direction as a, but 3 times longer than a. Minus 3a has the opposite direction to a and is 3 times longer than a. So 3a and minus 3a are negative vectors. And yeah, this is the general thing you'll need to know. If a is a vector and k is a scalar, then k into a is also a vector, and we are performing a scalar multiplication. There's something called as vector multiplication, but you won't have to know this until your A levels in further math. So right now it's not required. If k is greater than 0, then ka and a have the same direction. If it's less than 0, they have opposite direction. Because if you multiply it by -1, the direction changes. And therefore, if k is less than 0, it's going to switch direction. And if k is 0, then we're going to have a 0 vector. And therefore, if we have v, kv would be k into v1 and k into v2. And that's all you need to know for addition, subtraction, and multiplication. And now we'll solve questions based on this. These are the questions. Take a couple of minutes to solve them yourself, and then once you're done with that, I will work it out. All right. I'm hoping that you have solved these questions, and now I'm going to solve them. We have to find 3q. This is scalar multiplication, so this is going to be 3 into 2 minus 3. It's going to be 3 multiplied by 2, 3 multiplied by minus 3. This works like multiplication. It's not complicated. It's just very simple. And now we have to do B, multiplication. This is addition, and this would be multiplication. So B is 4, 1 plus 2 into 2 minus 3. We first multiply 2 into 2 and 2 into minus 3. We get 4 minus 6. And now we have to add the x components, which is 8, and add the y components, which is minus 5. That's how you do it. And now let's do C. It's half p minus 3q. We've already found 3q, so we'll just sub that in. But half of p would be this. It would be 2 and half, plus minus 6, 9. When we add these, we get minus 4 and 9 and a half. So this is how you do addition, subtraction, and multiplication. Time for this one. Suppose A is this, B is that, and C is that. We have to find A plus B. A is 2i minus j, and B is I plus 3j. We have to add the x components and j components. It's almost like, what is that? Like term addition. You know, this is I and I, this is j and j. You can't add these two, you can't simplify it further. So it's going to be 3i plus 2j. Let's do B. 3 into 2i minus j plus minus 4i. It's 6i minus 3j minus 4i. We get 2i minus 3j. Let's look at C. 2b minus a. 2 into I plus 3j minus of a, which is 2i minus j. It's going to give us 2i plus 6j minus 2i plus j. These get cancelled, and we're left with 7j. Now we have D. It's telling us to find the modulus of C plus A. When we say modulus, we mean the magnitude. So first we have to find C plus 2A, which is going to be minus 4 plus 4i minus 2j, and we'll have just minus 2j. So the magnitude is 0 squared plus minus 2 squared, which is 2 units. That's the answer. Here we have to find the magnitude of p in the first question. It's going to be square root of 1 squared plus 3 squared. We have square root of 10 units. And now let's do b. b is 2 into p, so square root of 2 squared plus 6 squared. Square root of 4 plus 36, square root of 40 units. You can simplify this further, but we can leave it like this. And let's do f, magnitude of q, so minus 2 whole squared plus 4 whole squared. We have 4 plus 16, so square root of 20. 4q is minus 8 16. The magnitude would be square root of 8 squared plus 16 squared. Let me work that out, which is 8 root 5 units. And now let's do this question. We have to do p minus q. So it's going to be 4 2 minus of minus 1 minus 5 minus 4 2 plus 1 5. It's going to be 3 7. Let's do b. Q minus r. And then we have b, which is p minus q minus r. Is going to be negative 3, so negative 6. 2 plus 5 plus 2 would be 9. And now try to solve the last question. It's going to be easy. Q is minus 4. No, minus 4, sorry. Minus 1 minus 5. 3 minus 2. And then minus b. We had 0 on top and minus 5 here. And therefore this is 0i minus 5j. And with that we finished this subtopic. And this is the next subtopic, the vector between 2 points. So here we're gonna try to find vectors when we are given two position vectors. If we want to find the vector AB, and if we're given OA and OB, we just have to trace to reach here. So it's like following a path. If you want to go from point A to point B, you can go from here to here, you can go here and here. So that's the principle we're going to use. So if you want to reach from A, if you want to go from A to B, we have to go here, and then we have to follow this path. So that's basically what we're doing. So we trace our way from A to O. That's going to be AO plus OB. But we can also rewrite AO as OA multiplied by negative 1. So these two are essentially the same thing. And therefore, if you're trying to find the vector AB, we have to do go from A to O and then O to B. Therefore, it's going to be OB minus OA. A small trick you can use is this. If you have vector AB, you can write OB minus OA. So you can write the position vector of the second letter, subtract by the position vector of the first letter. And that's how you derive this. So that's the quick method, but you can also use the tracing method. Either way, you're going to get the same answer. And now we're going to do some questions. Let's read the questions together. Let's look at the first one. Find AB given that the position vector of A is 2, 3 and the position vector of B is 4, 7. We know that vector AB is the same thing as OB minus OA. These two are essentially the same, and we have the coordinates for this and for this. So we just have to plug in the values. So let's write 4, 7 minus 2, 3. This is going to be 2, 4, which is also 2i plus 4j. You can do the same thing for the remaining questions. So this is going to be 1 minus of minus 1. So this is going to be B, question B. This is going to be 1 minus 3. Therefore, it's going to be minus 2 and 4 minus of minus 1, which is 5. C will be minus 1. No, now they have switched the B and A. So this is going to be 3 minus 2. So it's going to be plus 1. And then 0 minus 5 minus 5. D. This was D and this was E. So we have B, A. We have to do OB minus OA. So 6 minus 0 is 6, minus 1 minus 4 is minus 5. And it's that simple. Let's look at question number 2. Consider the point A with coordinates 1, 4. So we have to find the coordinates of B given that vector AB is 3 minus 2. This is also very simple. We have to first write the equation. Vector AB is OB minus OA. Let's plug in the values. AB is 3 minus 2. We don't know the coordinates of B. So let this just be OB. OA is 1, 4. Let's take this to the other side. So we get OB is 3 minus 2 plus 1, 4. It's 3, 2. 4, 2. So this is 4i plus 2j. Let's do the same here. Okay, this may seem confusing because we are used to AB. But like I taught you, CA would be the position vector of the second alphabet or the second letter, so which is OA. You have to subtract this from this OC. It's that simple. This is gonna be, so we have CA, which is minus 1 plus 2, and then OA is 1, 4 minus OC, which we're trying to find. If we move this to this side, to the left hand side, we get 1, 4 minus 1, 2. It's gonna be 2, 2. It's as simple as that. We have this diagram here with points such as B, C, M, and A. So A, B, C, and M. We have to find the coordinates of M. Alright, so when you use two dashed lines, that means that this length is the same as this length. And therefore, this is the bisector of this line. So point M is the midpoint of AB. This is pretty simple. You just have to add the x coordinates and divide that by 2 and do the same for the y ones. So if we want to find the coordinate of M, we have to do 3 minus 1 divided by 2. So that's going to be 2 divided by 2, which is essentially 1. And let's do the same for this. It's going to be 6 plus 2 divided by 2, which is 4. So the coordinate of m is 1, comma 4. The reasoning behind this is if you want to find the average of something, let's say we have a set of data. What do you do to find the average? You add them up and divide by the number of elements. And that's what we're doing here. If you want to find the midpoint, we have to find the average coordinate of the point. And therefore, this is going to be 1, comma 4. And then we have to find the vector CA. CA is OA minus OC. We know that OA is 3, 6, and then OC is minus 4, 1. This is going to be 7, 5. So CA is 7, 5. So 7i plus 3j. You can do the same for the remaining questions. So it's going to be CM is OM minus OC. And CB is OB minus OC. You can find these on your own. It's not that hard. And now let's look at part C. We have to verify that CM is the same thing as half CA plus half CB. Okay, I guess after all we have to find this. I will just work this out. CM would be OM, which we already have. And then OC is minus 4, 1. This is going to be 5, 3. And CB is OB minus OC. OB is minus 1, 2, minus. OC is minus 4, 1. This is going to be negative 1 plus 4, so 3, 1. And now let's verify this. We have CM here. Let me just highlight this. This is CM. So we have to verify this. So let's take half as a common factor. Let me use a different color. So it's going to be half times CA plus CB. Half into, we know that CA, where's CA? This is 7, 5 plus CB is 3, 1. It's going to be half into, this is 10 and this is 6. Just like basic multiplication, you have to multiply 1 by 2 with 10. So we get 5, 3. So CM is indeed half CA plus half CB, and therefore we have verified this. And that's it for this topic. Moving on, we're going to look at parallelism. This means that two vectors have the same direction vector. We're going to learn more about this in A levels if you're planning to take them. But here you just have to know that if two vectors are parallel, then they are multiples of each other. So you have learned that 4 and 2 are multiples of each other, meaning 2 into 2 is 4. Or also we have like 6 and 18. If you multiply 3 into 6, we get 18. And therefore, parallel vectors in the chapter of vectors means that they are like scalar products of each other, if that makes sense. All right, so let's just look at this example. So we have A and then we have 2A. The multiplication of 2 is what is different, meaning the magnitude of this vector is twice that of just A. And therefore, parallel vectors have the same direction but different magnitude. But they can also have the same magnitude, but it's not a condition for vectors to be parallel. The only condition it has to meet is that they have the same direction vector, which in this case is A for all these three. And therefore the magnitude can be different, but the direction vector has to be the same. And we have AB. So if A is parallel to B, then there exists a scalar value of K such that A is KB. That's pretty simple. It's time to do some questions. Let's look at the first one. What can be deducted from the following? We have A is 3 times the vector CD. Like we saw in the previous slide, this means that they are parallel vectors because AB is essentially a product of a scalar value k and some other vector. And therefore, A means that they are parallel vectors. This is slightly interesting. This is because although this is a scalar product or like a scalar constant that is being multiplied to another vector, we know that if we have A, this is vector A, this will be negative A, just to know the direction. It's supposed to be parallel, but yeah. Let's say this. This is negative A because it's in the opposite direction. And this also applies here because there's a negative sign in front of this. It means that they're anti-parallel vectors, meaning they are parallel but they face the opposite direction, almost like couple in physics. So like we have this, one force acts upwards, the other one downwards, and therefore they form a couple. And this is similar, one acts this way and the other, maybe the magnitude might be different, so it doesn't matter. So these two are still parallel, but they are somewhat anti-parallel because they're in the opposite direction. And now this is the same thing as this. So yeah, they're parallel vectors. And now we can look at this. We have to find R given that A is this and B is this and that they're parallel. Okay. We have this, right? We know that they're parallel, meaning A is KB. This is the notation for a vector, or you can use like an arrow, or you can make the letters bold, whatever you want. So A is 2 minus 1 K into negative 6R. We can equate the top half of the equation, so it's 2 is minus 6K. And the value of K is negative 1 by 3. And now we know that negative 1 is K into R, and it implies that negative 1 is negative 1 divided by 3R. So if we want to find R, we multiply this here and divide by negative 1. We end up with 3. So therefore, the value of R is 3. This is also a very similar question. It's A equals KB. And now A is negative 1 R and K multiplied by 2 minus 3. Negative 1 equals 2K, or K into 2, and we can deduct that K is negative 1 by 2. And if we want to find R is basically negative 1 by 2 into negative 3, which is basically 3 by 2. And that's how you solve a question like this. Okay, I think this is the last question. We have to find the vector v, which has the same direction as 2 minus 1 and length of 3 units. This basically is telling you that the magnitude is 3, and therefore we can say k multiplied by 2 minus 1. If we find the magnitude of this, which is basically square root of 2k whole squared plus negative 1k whole squared, is essentially 3. And therefore we can expand this. The first question is very simple, but it's gonna get complicated as you solve harder problems. So we have 2k whole squared plus, this is essentially plus 1 squared. So it's k squared, which is 9. We have 4k x squared plus k squared, which is 9. And this is going to be 5k squared equals 9. And k squared, square of k will be 9 by 5. And k will be plus or minus 3 root, 3 divided by root 5. Okay. So we have to find the vector v, right? And therefore it's going to be 3 root 5, 2, and this is going to be 3 root 5, negative 3 root 5. 3 by root 5. We can't write k as negative 1 because that means it's going to go in the opposite direction. So therefore we have to reject the possibility of negative 3 by root 5. Therefore, this is our final answer. Here, I want you to try this out for yourself and see where you go. And here it's in the opposite direction, meaning here we have taken plus or minus, but here we have to do negative because it's going in the opposite direction, right? And therefore, it's going to have a very similar answer, but when you do square root of whatever you get, here, you have to take the negative value. And that's basically it. So we have reached the last topic here, which is unit vectors. This is pretty simple. There's not much in this. You just have to know the formula and why it's used. So a unit vector is often used to give you the direction. So if it's basically of magnitude 1 and it will show you the direction of the vector. That's why unit vectors are used. So given a non-zero vector A, its magnitude, which is modulus of A, is a scalar quantity. If we multiply A by the scalar 1 divided by the magnitude of the vector, we obtain a parallel vector with unit 1. Like I told you, we use this to show the direction of the vector. Since they are parallel vectors and magnitude doesn't matter, we're trying to indicate the direction of the vector. So a unit vector in the direction of A is 1 divided by the modulus of the vector multiplied by the vector. And a vector of length k in the same direction of A is k divided by the magnitude of A multiplied by the vector A. It's basically that. And they're parallel and they could be plus or minus. I told you, right? It can either be parallel or anti-parallel, meaning they act in the same line, but they face opposite directions. So that's what I mean by anti-parallel vectors. And that's it, I can give you an example also. If, for example, find the unit vector of, let's say, 3i minus 4j. What do? We have to, first of all, find the magnitude. No matter what, just find the magnitude. So let's say this is vector c. This is this. So the magnitude of c is going to be the square root of 3 squared plus 4 squared. That's 9 plus 16, which is 5. And therefore, the unit vector is 1 by 5 multiplied by 3 and then 3 minus 4. So that's basically it. That's how you find the unit vector. It's as simple as that. And with this, we're done with the whole vectors topic. And it's best if you go through this video. If you want to do it again, and then go to your textbook, solve all the questions, do some past papers, find questions. Like, I think it's online where you can like find topical questions where you can solve questions based on a particular chapter, and that will actually help you maximize your score. So all the best, and hope to see you in the next video.